All right, everybody. So yesterday we talked about glycoside formation, and I gave you the example in class of O glycosides, and then I said this can be done with nitrogen nucleophiles as well. And this is an example of an N glycoside. So let's go through and do the mechanism really quick. We've got glucose here. Does it matter what glucose we start with? No, it doesn't matter what glucose we start with. So I'm just going to draw one of the glucoses.
So okay if we started with it in a ring?
If what?
If we started with it in a ring instead of linear?
So remember, in this one, it's going to be cyclized in order to do the glycoside formation.
Right.
But it's always going to be in...
I was asking if we had to show the cyclization.
No. Yeah. All right. What's the first step? Protonation. So I'll just write H+. So we can protonate this alcohol. So now we've converted that into a good leaving group. Okay, there's a lot of side conversations going on. Let's make sure we can all hear. All right, we can dump down electrons, kick off our leaving group. All right, so now this oxygen has a positive charge. Yep. For chair structures? No, that's a fair question. So what I do is I do offset parallel lines kind of diagonally, then I do another offset parallel lines diagonally, and then connect the corners. It takes practice. All right, so let's do the next two. Oh. All right, so if we have aniline, this aniline can attack from either face. It can attack from that bottom face, or it can attack from the top face. So I'll say or top side attack. I don't want to have to draw it twice. All right, so we've got our precursor. And then last step, I'll also write plus epimer. Would be deprotonation. And we get both of our products.
Would the water deprotonate it?
In this case, water could deprotonate it or aniline. It's all under equilibrium conditions. We've got OH, 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 and I'll just write plus epimer. All right, so for the epimer that I have drawn, is this alpha or beta? Yeah, I've drawn the beta one. We could also draw the alpha one too. Remember, the epimers are just a specific type of diastereomers where only one stereocenter is flipped. So I wouldn't say plus diastereomer because that's not descriptive enough. We'd want to say plus epimer. All right, so let's finish up carbohydrates. And I'm going to kind of trim down the carbohydrate section a little bit. You guys are welcome to copy these down if you'd like, or you can print them from the lecture notes online. I just don't like having to draw polymers of carbohydrates. It takes forever. All right, so the first disaccharide that we have is maltose. All that a disaccharide means is two sugars, right? Equals two sugars. Nope. Thank you. All right, so we've got two sugars linked together. We've got a whole variety of these, but I'm just going to list the most common ones. If we look at maltose, we've got two different groups. We've got this sugar. Does anybody remember what this one is? Yeah, it's glucose. And specifically, it's got an alpha position on the anomeric carbon right down here, so we will call it alpha D-glucose.
Does the group coming off of the anomeric carbon make like the name? Does that distinguish what the name is going to be, or no?
That determines alpha versus beta.
I mean, I understand the position of it, but the actual molecule itself. When it was or the aniline, it was alpha
And so in this case, it's an O-glycoside, because in this case, we don't have a hydroxyl group in anymore. We actually have a new ether linkage, so it's more of an acetal. So in this case, we would call this a glycoside bond between these two. So it's an O-glycosidic linkage between these two sugars. The second sugar is also alpha D-glucose. And the interesting thing is with this second glucose, the one on the right, is that this can ring open and act as an aldehyde. So we can basically say this can ring open to an aldehyde. The other anomeric carbon on that second sugar to the left cannot ring open, therefore we can only do chemistry, at least carbonyl chemistry, on that anomeric carbon. All right, if we look at lactose, it's a little bit differently, or it's a little bit different. I can't talk today.
Why does it ring open? I'm sorry, I was trying to draw this thing.
So remember, this is hemiacetal, right? Hemiacetals can ring open and ring close. So glucose can be linear or it can ring close. It prefers to be ring close, but a little bit of this in equilibrium will ring open. All right, so with lactose on the left-hand side in the green box, what we have is beta-galactose. That's one of our family tree carbohydrates. And we've got beta-galactose attached directly to alpha D-glucose. Oops, sorry, thank you. So we've got beta D-glucose. It's also beta D-galactose too. So you can see that these sugars can not only vary in the identity of the two sugars that are attached together, but it can also vary in how they're attached. Are they attached in an alpha orientation or in a beta orientation? Yep.
So is that called galactose because of the orientation of that in there?
So galactose only differs in this hydroxyl group. So it's very, very similar to glucose. It's an epimer of glucose.
And it's only because of the being axial.
Yeah, exactly. So all the different sugars have different stereo centers around the ring. All right. In this case, we also have another carbon that can ring open to form an aldehyde. And so these two can ring open and act as a carbonyl group, and we can reduce them or oxidize them and whatnot. All right. There's one last sugar.
Okay, I just... we know we can't draw these.
That's why I was saying I would really recommend for these just print them from the class notebook. All right, so this side we've got glucose, and in this case it's alpha D-glucose. And over here we have fructose. And so this disaccharide is called sucrose. Does anybody know what sucrose is? It's table sugar. So the table sugar we have actually is 50% fructose, roughly. So this is table sugar. The interesting thing is that some people actually lack the enzyme that's capable of cleaving this glycosidic linkage. Exactly. So if you're lactose intolerant, you don't have this enzyme, you get a big buildup of lactic acid inside of your body. You feel pretty uncomfortable if you eat too much. You often get super gassy too. Sucrose, on the other hand, has this alpha connectivity. Our enzymes have a much, much easier time breaking alpha connectivity between two sugars. So this alpha glycosidic linkage can be cleaved much more readily than a beta linkage. The other thing to notice too is that these are called 1,4 linkages. So if you actually look at the numbering around the ring, we can label this 1, 2, 3, 4, 5, 6. So the anomeric carbon is 1, and then we go counterclockwise, or I guess clockwise all the way around to 6. And same thing down here, we go 1, 2, 3, 4, 5, 6. Oops, sorry. What's that?
Isn't the 6 a carbon, not the oxygen?
Oh, thank you. Sorry. All right, so when we're looking at these, we call them 1,4 linkages. You can actually get substituents with different linkages than 1,4, and we'll actually talk about some carbohydrates that have differing linkages.
What's the A for?
Right for a second.
Why does it say A14?
That's alpha 1,4.
I called the alpha the A.
Oh, that just is saying a, like
The verse.
a dog, a cat. It's just a pronoun. All right, so these are simple sugars. The main sugar that we metabolize is glucose. So even if we eat sucrose, we cleave it, and then we metabolize that glucose. There's a lot of people saying that diets that are high in fructose can mess with your metabolism. So if you hear people debating about high fructose corn sugar, it still is mostly sucrose, but it has slightly higher percentage of fructose in it. There's a lot of people trying to link that to obesity. There's a lot of debate about it. The reality is sugar is bad for you almost regardless of the source. So it's more just cutting out sugar from your diet. That's the big thing. All right, let's... No, but the problem is when you've got a 5-year-old going to school with a 20-ounce Coke, that's a problem.
Their parents need a beat down. That is not okay.
All right. All right, so polysaccharides are the polymer versions of saccharides. This is the most abundant saccharide on our planet, cellulose. It's the stuff that makes up all wood, makes up a huge portion of plant matter. And this is just repeating glucose units. So you can see all of these are glucoses.
So because those are the main things that why it's so hard for us to digest cellulose?
Yes, exactly. That's what I was just going to say. So humans lack the enzymes that can cleave these beta position bonds, but what animals can? Cows. So cows don't necessarily have the enzyme. Exactly. What they do have is they have bacteria in different portions of their stomach that have evolved to cleave these bonds. So the big push right now, it could make you an instant billionaire if you figure this out, is how can we take all of this plant matter, like yard clippings and things like that, and convert it into glucose easily, and then ferment that into ethanol and put it into cars. So there's been a ton of people working on this. The problem is it's really, really difficult. It's not as easy as we thought it would be, and so they've been spending about 40 years trying to make this commercially viable.
40?
Yeah, over 40 years even. They've been working on this practically as long as we knew.
Alcohol, you said?
Yeah, so when you think about it, if we can cleave all of these into glucoses, we can take this glucose, ferment it into ethanol, because we can ferment ethanol or sugars into ethanol, and then we can burn ethanol as a fuel.
Aren't they doing that with corn or something?
Exactly. So they're doing it with corn ethanol, but corn actually makes simpler sugars that are much, much easier to convert. So high fructose corn syrup, they're fermenting that essentially. Yeah, so it's a really interesting thing. The problem with corn as an ethanol source is most of the cellulose byproduct just gets tossed away. They don't use it. If we could figure out a way to use that, it'd be very, very economical. So that's one polysaccharide. The next polysaccharide we have has a bunch of repeating beta glucose units. And this is called amylose. this is the main component in starch. So it's still repeating glucose units, but in this case it's a 1,4 alpha connectivity. And our enzymes can cleave these. So this is the starch that's in potatoes and a lot of our starchy foods like carbohydrates, or like pasta carbohydrates, things like that. It's not as simple as it looks. Most starch actually has this 1,6 connectivity down here. So like I said, not all starches are connected in a 1,4 manner. A lot of starches are actually connected in a 1,6 branch. So you may have a long chain that's 1,4 connected and an occasional 1,6 branching unit. So starch has 1,6 branching. I guess it says it right there. I didn't need to rewrite it. All right, the other thing that's interesting to look at too. So let's go back to our cellulose. So if we look at cellulose, cellulose is this long chain. It doesn't face a lot of branching. Yeah?
So, you have to withdraw all these different chains.
Yeah, you have to, a really long one.
I'll just ask you to do a few cellulose strands. Yeah. Cellulose, if we look at it, is usually unbranched. It can hydrogen bond very, very tightly with neighboring cellulose strands. That's actually one of the main reasons why it's hard to digest, is that it's hydrogen bonded into a brick. That's why wood's so tough. But if we go over and we look at starch, starch has these big branching units coming off of it. Things that are branched can't stack as easily. They don't hydrogen bond as tightly. That's why we have soluble starches even. So if you boil potatoes, you can see the water turn murky.
Yeah.
That's the starch coming off your potatoes. Branching things don't tend to hold onto each other as tightly as a long linear cellulose unit. So it's interesting to think that just the difference between an equatorial and axial position determines whether or not we can eat something. Yep. You mean between the 1,4 units? It'll be pretty close to 109.5 because they're still sp2 hybridized. It'll probably be more like 104 because you've still got those lone pairs in there. For cellulose, yeah, it's just different. It's hard to imagine without a three-dimensional model. I'll try to see if I can find a three-dimensional model for you guys.
But even though the modules look different over here on the jellies, they're actually really similar.
They are similar. One's just pointed in an equatorial and one's in an axial position. Yeah, that's a good question. All right, one last polymer, one of my favorite polymers, chitin. Yeah, so if we look at insects, insects have evolved, basically turned what used to be cellulose into an amino sugar that has an acyl group coming off of it. Yep, and they use it as a skeleton because it's incredibly strong. So it's an N-acyl amino sugar. It's a derivative of glucose. So again, we can't digest chitin very well. It's not a great food source. But the interesting thing is they actually are talking about harvesting insects for food. Does anybody know why?
Great source of protein.
Yeah, exactly. So this is completely, it's not in our textbook, but it's something that's fascinating to think about. They were talking about raising cattle. Cattle takes a huge amount of water to get 1 pound of beef. If you look at crickets, it takes nothing to raise crickets. Crickets can practically absorb water from around them. You don't have to give them much of anything. So they're talking about using this as a dietary supplement. Yeah, cricket flour is the big deal. All right. So to kind of wrap up our chapter, we covered a bunch of different reactions. This was the reaction that Adrian was talking about. If we have an open chain Fischer projection, we can show it in this Haworth projection. This can attack in, and we can actually form our hemiacetal, shown in the closed ring form. Sugars prefer to be in closed ring. You should be able to draw this mechanism of hemiacetal formation. That's review from previous chapters. This can also be done with shorter rings. and actually form a furanose ring. That's a 5-membered ring. And then we also covered a whole variety of reactions with sugars. The first one was acylation. Second one, methylation. Third one, we form our O-glycoside, really similar to our problem of the day. Next one, we can reduce an aldehyde in the open chain form, or we can oxidize it, or we can doubly oxidize it. Yep.
Do you need to know the names of all the sugars on the handout? that you
No,
guys are-
you do not need to know the names.
Dr. Engel, I don't remember learning all this. Did you teach us all this?
We did cover it yesterday. I would review.
All of it?
Yep.
But that map right there is something you should know.
Yeah, and like I said, you can go online and print this out too, or come to my office and I can get you a copy. This is the same chart in the back of your book. All right, the next one we covered was interconverting between sugars. You can either add a carbon on using cyanide, and we get a pair of pepimers, and then you can reduce your cyanohydrin, or you can do a, shoot, I'm forgetting the name, it's something degradation. I'm really spacing right now.
So we don't need to know.
Wool, yeah.
Wool.
W-O-H-L.
Yeah, the wool degradation. I always forget. I want to say Wolf-Fishner, and I know that's not right. So you form your oxine, and then you can treat it with sodium hydroxide and get one carbon removed from there. All right, so let's keep our wheels on the ground. Introduction to amino acids, peptides, and proteins. Yay! I know, it's bio. Now it all makes sense. All right, introduction to amino acids. So amino acids are pretty simple.
Yeah, that's.
So when we draw an amino acid, we usually draw it with an R group like that. We call these alpha amino acids. Why do we call them alpha amino acids?
They're on the alpha position.
Exactly. So it's not a beta amino acid. That amino group's coming off the alpha position, so it's alpha amino, indicating that alpha position is the amine is separated one carbon away from the carboxylic acid. Why are these important?
So we're looking at the alpha to the amine or to the carboxylic?
Well, just why are amino acids in general important?
No, I'm just asking about the alpha.
Yeah.
The alpha position, are we looking?
Yes.
Yes, proteins. Yes, the alpha position is one carbon away from the carbonyl.
Oh, I know. I mean,
Yes, Adrian.
Okay, thank you, Ian.
All right.
Dr. Engel's all listening.
All right, so let's draw a short peptide unit here.
Oh my gosh, sure. Yeah.
This is it. So we've got an R group here. We've got an R group here. We've got an R group here. Essentially, a peptide is just repeating units. Oh, no. And what we call these are peptide bonds. It's a bond between two separate amino acids or even two of the same amino acids in order to form a polymer. And so we call this a protein, or some people call it a polypeptide. It depends on who's teaching the course. What's that?
Since you're drawing like triple arrows, do you know the reactants or is it?
I'm just showing 3 arrows because you can repeat it. We'll talk about how to make these, though. It's not as simple as you would think to form a polypeptide. Our body's excellent at it. Synthetic chemists are not so great at it. We have very elaborate techniques to make peptides. All right, so one thing I did post on the class website is another chart you have to remember. All right, I'm kidding. So If you go on and you take biochem, your instructor may ask you to memorize all of these. Because we only have a week left in this term, I'm not going to ask you guys to memorize these. But this is a fantastic chart. I put a PDF link of it online. I didn't print it out because our color printer died downstairs. I'll try to get copies to you guys next Monday, though. The best part about this is that it not only shows the 20 main amino acids, but it also kind of divides them up into groups, and we'll talk a little bit more about these, but there are some amino acids that are more acidic than others. There are some that are more basic than one another. There are some that have aromatic groups, some that have aliphatic groups, so you can kind of break them apart using this visual chart. So it's a really nice tool to use. Honestly, the 20 here are only some of the amino acids out there. These are the 20 natural amino acids in humans. There's actually a few derivatives of them, too, where you've got selenium in there instead of sulfur. And those are some other fancy ones. And then plants make a bunch of goofy ones, too, that don't tend to fit into this chart. So this is just the most common ones in humans. So if you're taking biochemistry, these are the ones you'll see.
What is aliphatic?
Aliphatic just means alkane chain on there. Mm-hmm. All right, so let's draw some amino acids. So amino acids can be drawn with a Fisher projection. So just like with sugars, we can draw these out. So I'm going to draw a couple of them. So I'll have a methyl group down here. So CH2OH. Sorry, let me finish drawing all of these and then we'll talk about them. So we've got HOH, HOH. And what we have going left to right is we've got alanine. We've got serine. And we've got valine. All right, so just like with Fisher representations, remember the backbones are pointed back? Yeah, it's the cat on its back with the arms pointing forward. If we were classifying these D or L, what would these be classified as? L. So normally sugars, we have a hydroxyl group on the right side.
D or L.
So you remember with sugars, we said that D sugars always have the hydroxyl group over here. But with amino acids, these hydroxyl groups are actually on the opposite side. So we always call these L sugars, or sorry, L amino acids. And that refers to the left side of each of these. Does it have anything to do with chirality?
Yes.
Not exactly, because the identity of the R group could change the RS. And that's one big misconception a lot of people have, is they'll say amino acids all have the same stereochemistry. Not true. Amino acids are all L, but they don't necessarily have the same stereochemistry. The identity of the R group can change that from an R to an S stereocenter. So you do have to be careful with that. All right, I've got an interesting article. It's not, these aren't hallucinogenic mushrooms. So I was reading about this, you guys. So in China, they had this problem with people going out picking mushrooms and then hurling over dead. And they couldn't figure out what it was in these mushrooms that were killing them. And oftentimes, natural products scientists, whenever they find a toxic compound, they want to know what it is, because that compound might have some therapeutic uses in low doses. So in this case, they went out and they searched for these mushrooms in China, and they found them. They killed 260 people. Pretty incredible. And so they kept on trying to figure out what is it in these that are killing them. And they found these amino acids in there. So you can see they're all alpha amino acids, and then you've got a guanidine unit on the right-hand side. But the problem with these is that these are D-amino acids. So they're not the correct type of amino acid that our body is used to dealing with. So what do you think happens when these get introduced into our body?
You die.
Yeah. So your proteins fold in a really, really specific manner. If you put in an opposite-handed mimic to one of your amino acids, it's going to kink up all of your proteins. So these are some of the most toxic compounds known to man, just simply because they're the wrong type of amino acid. And so you do have to be careful. The syntheses that I'll show you for making amino acids are racemic. Oftentimes you have to be very, very careful purifying these to make sure that there's no trace amount of the D amino acid left over, or else you could end up killing people. There's a lot of advanced techniques to avoid D amino acids.
Why do people keep eating them if people are dying? Like,
Well, honestly, people do that here too. They don't know what they're picking. So it's just mushroom identification. So if you do want to read about this too, I put the link on here. It's kind of interesting. All right, acid-base chemistry, you guys. We're going back to the basics. So let's say we've got an amino acid here. And we put this into our body. So our body has a very tightly controlled pH system. Do you think it's going to look like the amino acid drawn on the left?
what? I'm sorry?
So will it look like the representation of the amino acid that I've drawn?
No.
Yeah, we've got an acid here, and we've got a base there. So we're going to do a proton transfer. So you mostly end up with your protonated amine, and your carboxylate salt. What do we call it when you've got a positive and negative charge on the same molecule? Yeah, it's Vitter ion. People will also refer to these as amphoteric molecules, meaning they can either act as an acid or a base depending on the conditions. And each amino acid has very different pKa's, because these R groups can play a very, very big role in the acidity of not only your carboxylic acid, but the acidity of your ammonium ion once it becomes protonated. So the pKa's do matter a lot. If you go into your chart, or in your book, sorry, table 25.2 has a list of pKa's for your carboxylic acids. And ammonium ions. I'm always blown away by how much they differ. Some amino acids are very, very basic. Other ones are very, very acidic. It really depends on the situation. There is an interesting thing I did want to bring up, and this is called the isoelectric point. So isoelectric point is the point at which, or the pH at which the Zwitter ion is in its highest concentration. At its highest concentration. And the calculation for the isoelectric point is actually very straightforward. And this is called Pi. That's the isoelectric point. It's the pKa of your carboxylic acid plus your pKa of your ammonium ion divided by 2. So you just average the pKa's of those two, and you can figure out the pH at which you have primarily your Zwitter ion. Some people get confused by this, but this is your pH of isoelectric point. The cool thing with this is you can actually separate out amino acids by adjusting pH. So what you can do is change your pH, make sure that one of them is Zwitter ionic, the other ones will be mostly positive, mostly negative. And then what could you maybe do to separate them if you can change the charge of various molecules? Yeah, electrophoresis. So have you guys done that in biology at all? I think some of you guys have. So it's the idea of applying a current to these molecules, and if you have a negative bias at one end and a positive at the other end, you can actually separate out these amino acids at a particular pH. So this is one way of purifying amino acids and trying to isolate a specific one. Oh. So can purify, I'll say amino acids with AA. Electrophoresis. This isn't the main way people purify amino acids anymore, but you can still do that. What's another way we could purify amino acids besides gel electrophoresis? We did it in our spinach lab. Yeah, chromatography. Chromatography is usually used for separating these compounds, and you can actually get special silica. It's similar to alumina that's designed for amino acids, and you can purify them very, very easily that way. All right, so let's jump into synthesis a little bit. I don't think we'll make it through this whole section, but a lot of it is review. All right, so amino acid synthesis. All right, the first one should look pretty familiar. Volhard-Zelinsky. And if you forgot about this, it was from chapter 22.2. And it's a pretty straightforward reaction. We take a carboxylic acid and we want to alpha halogenate it. What reagents do we need in order to do alpha halogenation of a carboxylic acid?
PBr3, bromine, and then
Yep, and then acid or water, and it's good enough. So this was one of the ones on our exam that people were struggling with a bit, but hopefully we remember it now. The tricky thing with this reaction is you end up scrambling stereochemistry. You don't get an enantiopure compound. So this is racemic. And then in the next part, what we're going to do is react this with ammonia. So excess ammonia. And what do you think we can do with that bromine? Yeah, we substitute it, right? It's not a great electrophile. It is fairly hindered. But in this case, it's actually beneficial that it is hindered. Why is it beneficial that that electrophile is hindered?
slowly react.
It's a slow reaction. So we said normally with amines, if we were react them with a primary alkyl halide, we'll get over-alkylation. In this case, we can actually stop with one amino group on there. And this is what makes this reaction better than what we would anticipate. We still have a racemic mixture. The last step we want to do so we don't accidentally kill people is purify it. This is something the book kind of glosses over. And once you purify it, you can get one enantiomer out, and you would probably just discard the other enantiomer. This was the old school way of making peptides. It's not commonly used anymore, but it's historically relevant. The problem with this is you immediately limit yourself to at most a 50% yield, assuming you got 100% yield and everything else.
Did you mean put an R on the way?
Oops, sorry, that should be an NH2. Thank you. All right, we've got one last one I'll show you guys, and then I'll let you enjoy the sunshine. This is a malonic ester variant. All right, this again was from chapter 22. So malonic ester looks like this, but we're going to use a variant of this. And this can just be purchased. We don't have to make this. This is called diethyl.
Somebody has to make it.
It's cheap. Acetamido. There you go. All right, so now we've got this starting material, pretty easy, cheap to purchase. What can we do with that alpha position? Yeah, just deprotonate it. So let's use sodium ethoxide. We want to choose the appropriate base, and then we can alkylate it. I'm going to abbreviate the acyl group. Okay, so now we've done the alpha alkylation. What's the next step for the malonic ester synthesis? We want to get rid of one side, right? How can we get rid of this whole side?
Like acid and heat.
Yeah, decarboxylation with acid and heat. And now when we do this, you can also deprotect your acyl group. So let's highlight everything that's getting popped off in this step. All of those groups get removed during the acid workup.
Where did the AC come from?
An acyl group is, let me circle it. An acyl group is this guy. I just abbreviated that as AC. And then in the last step, we purify. So it's a pretty clever variant on our malonic ester synthesis. All right, we'll continue on tomorrow with more synthesis reactions with amino acids, and then start, or not tomorrow, Monday. And then we'll get into synthesis of peptides too. All right, have a good weekend.